So hey everyone, thanks for coming. My name is Mohammed Abdel Fattah. I'm normally at Cornell Tech, but I'm here. It's my great pleasure to introduce Bill Daly. So Bill joined NVIDIA in January 2009 as chief scientist, and now he leads the research lab and reports directly to the CEO, and was there for this meteoric rise of NVIDIA as an AI company. Before that, he was chairman at the ECE department in Stanford, and before that, he was at MIT. Bill really needs no introduction. But I'm really happy he's here. I also learned a lot of things about him. He's a really cool person, actually one of the coolest people I've met in a while. One thing is that he was born in Ithaca. I don't know how many of you know that. He didn't really live here, but he was born here. He flied his own plane to come here. He races cars. He fixes cars. And there are so many things just makes him a super cool person who's had a real impact on the world. After this, he's going to Washington to have an impact on our government in the area of AI. And so I couldn't be happier that he's here. Please help me welcome Bill Daly. So.
Thanks, Mohammed, and it's hot in here. So, sorry for the delay. My laptop has decided to die on me at a very inopportune moment. But fortunately, the presentation is on the web. So it's a real fun time to be a computer architect and a hardware engineer because things are happening very quickly. And unlike sort of the period of time when Moore's Law was in effect, and you can kind of be a lazy hardware designer and process technology, we just make things better every year. Now that Moore's Law is over, we actually have to think hard and be clever. Of course, we have AI to rely on. So when it came time to do this talk, I typed into ChatGPT, please prepare a talk on trends in deep learning hardware. ChatGPT came up with a bunch of really, bizarre stuff that I wouldn't agree with. So I said, okay. I changed the prompt. It's all about prompt engineering. And I typed in, what would Bill Daly say about trends in deep learning hardware? And this is a response of ChatGPT, which is not too bad, but I decided to do it a little bit different way. And I'll start with a relatively recent headline. This was in the Wall Street Journal, November 8th. So, just about a week ago. And is actually a result of an interview I gave to a Wall Street Journal reporter. And it talks sort of about, how do we continue scaling GPU technology? If you want a lot of the details, you can read this article. I'm going to give sort of a headline service for a bunch of this in the talk. And next slide. Day of technical issues. There we go. So everybody these days is kind of interested in large learning models. This is sort of my cartoon about how large learning models work. And what they really do is that they distill data into value or into insight. So you start out with an enormous data set. Our data sets now are more like 10 to the 13 tokens, 10 trillion tokens. And a token is slightly less than a word. You wind up with somewhere between 1.5 and 2 tokens per word going through the tokenizer. Or if you're doing an image network, we typically have billions of images, often close to 10 billion images these days. To put this in perspective, when we started playing with vision networks back in the early days of ImageNet in 2011, 2012, a 10 million image data set was a big data set. And today that's considered, too small to do anything interesting. And so you start with a model. The big models today, things like GPT-4 are close to 2 trillion parameters. Those are the things you have to learn to make the model useful. You start with a lot of data and you train. And training one of these big large language models is getting to be, I did the slide some time ago, it's getting to be for the really big ones, $100 million endeavor. It's $100 million of GPU time to train a big model. And that's why a lot of the companies that do this don't open source their models. They just spend $100 million. They're not going to give that to a competitor. Fortunately, Meta is giving their models away, which is nice of them. So anyway, after you train the model, you can think of that as taking your model and sending it to get a liberal arts education. It now has probably heard as many words as any human being hears in their entire lifetime. And it used that to kind of train its parameters, but it's general knowledge. And so to be useful, you'd like to fine tune your model. So I gave a keynote at ICCAD a couple weeks ago, and I talked about a model we have fine tuned by taking our internal design documentation since the founding of NVIDIA and feeding it into the model for what's called, sort of specialized pre-tuning. And you're basically just training the model some more on a specialized data set. So now our model knows all sorts of things about GPU design. And so we actually save our senior designers a lot of time. If a junior designer has a question about, how does the texture unit work, it can ask that question to this thing we call Chip Nemo, our internal large language model, and it usually gets a pretty good answer. Now, once you got the specialized model, and you can specialize it for a lot of things. You can specialize it for writing code, for giving medical advice, to be a tutor for education, writing creative things, chip design, which is what we use it for. Once you have that specialized model, then the way you, and by the way, I should say that this fine-tuning endeavor is something that doesn't require, tens or hundreds of millions of dollars. It can be done for anything as low as a few $1,000s to a really large fine-tuning job, might be $1 million. And I should add also this block here. One of the things that really pushed ChatGPT over the line was also training it with human, feedback reinforcement learning, where it would basically generate multiple prompts. Then you would have human judges grade those prompts, thumbs up, thumbs down, or giving it a numerical score. And by doing that, the model then learns how to give answers humans like. And that really made it much more useful for human endeavors. And so now you have the specialized model, and you like to have people ask it questions like, how does the texture unit work? And then you go through this inference process where it's very quick. It's millicents per word to get an answer. And for a while, you had this problem that these models would hallucinate. They just make stuff up. If you asked them a question they didn't know, rather than doing what a reasonable human being would do, which is say, I don't know, it would say, oh, here is the answer you want. And there was some lawyer who got in a lot of trouble by having this, write his, legal brief, including all these citations to case law. Well, it turns out none of those cases ever actually happened. They were all made up, and the judge got very unhappy with him. And so one way of getting around that, and this is actually a recent addition to this slide, is to have retrieval augmented generation, or RAG, where you first take your query and you use it to query a database. You then pull out all the relevant documents, and you feed those relevant documents back with the original query into the large language model. And now it tends to actually answer things truthfully because it can point to the source documents and give you, information directly out of them. So let's talk a little bit about motivation and how we got here. So deep learning was enabled by hardware. I like to think of deep learning as having kind of three ingredients, the fuel, air, and the spark of deep learning. Well, the fuel in many ways is data. And we had large labeled data sets by the early 2000s. This is sort of a cartoon of the ImageNet data set. Pascal was actually around even before ImageNet. And the air is kind of the algorithms, the deep learning models, and training them with backpropagation, stochastic gradient descent. These algorithms have been around since the 1980s. Deep neural networks, convolutional neural networks, stochastic gradient descent, backpropagation were all developed in the 80s or earlier. Some of them go back to the 60s. But nothing really happened. And the reason was the third ingredient, think of the spark that ignited the fuel in the air, was enough hardware horsepower to train a large enough model on a large enough data set in a reasonable amount of time. In this case, it was the 10 million image ImageNet data set on AlexNet, which is a model of a few tens of millions of parameters in 2 weeks. That was done on 2 Fermi generation NVIDIA GPUs. I got introduced to neural networks when I was a graduate student at Caltech in the 80s. When John Hopfield came and spent a sabbatical there and taught a course on neural networks. And I remember training neural networks on little HP computers that were probably, their peak performance were probably measured in maybe, 10 million operations per second. Whereas here we have GPUs with, pushing peta operations per second. So there's, nothing like many orders of magnitude to help you there. And we need those orders of magnitude because since that sort of AlexNet moment when, people, that sort of available hardware ignited the fuel or mixture, people's ambitions have grown with what they want to do with neural networks. And during the sort of vision network thing over, sort of the 3-year period, shown here, 2013 to 2016, maybe a 4-year period, we got 2 orders of magnitude. So sort of an order of magnitude every 2 years in demand for GPUs. But since large language models started to appear, the Attention is Everything You Need paper came out in 2017, and BERT a couple of years later, about a year later, things have been increasing about an order of magnitude per year in demand. GPT-4 is a closed model. They haven't published the details of it. It's a mixture of experts model. It's about 2 trillion parameters. And our estimates are it takes about 10 to the 6 petaflop days. That's a day on a petaflop machine to train that model. So over this period of time, there's a 10 to the 8th increase in demand. And we feel, as the developers of the dominant hardware that's used for AI, tremendous pressure on us to continue to increase performance because we're gating the progress of AI. People would do more. They'd run larger models on more data and get more interesting results if they had more hardware. But we're no longer getting anything out of process technology. So how do we do this? Here's sort of a history of NVIDIA GPUs used for AI. And things, things actually started with Fermi. That AlexNet was run on Fermi, and AlexNet happened kind of back before this timeline begins. But when we really started getting involved in AI, our GPU was Kepler. But Kepler wasn't designed with this in mind. Its design was frozen, in probably 2010. And, it was designed for doing high performance computing, for which it had double precision floating point, and computer graphics, for which it had single precision floating point. And so, if you were doing deep learning on it, you're using FP32. And the biggest instruction it had to help you with deep learning was a fuse multiply add, or FMA instruction. And it got, 4 gigaops of performance, running these are tera operations per second. So, 4 teraops of FP32 performance. As we move down this timeline, the innovations fall into a couple of categories. I'll actually introduce with the next slide. But over this 10-year period, we got a 1,000-fold increase in performance from about 4 teraops to 4 petaops. And let me go through the dominant reasons for this. And the biggest one is number representation. So it turns out FP32 is vast overkill for doing deep learning. We can do a lot with 16-bit or 8-bit or even 4-bit inter FP. And the cost of doing math scales quadratically. You think about it, multiply as a dominant operation. When you do a multiply, every bit ands with every other bit, and you get a quadratic number of partial products. So you then have to sum up to get the answer. So a 32-bit floating point number is not 4 times as expensive as an 8-bit floating point number. It's 16 times as expensive. And the real gains we've gotten from going from FP32 in Volta to FP8 in Hopper is the 16x from that scaling. And it's interesting because at 2017 at ISCA, Dave Patterson gave a talk about the Google TPU, and he was arguing, all of our advantages for the TPU are because of its specialization. But in fact, if you look at its gains over, and of course he compared to Kepler, even though it's in 2017, he should have been comparing to Volta. All of its gains compared to Kepler can be attributed to the fact that he was comparing an int8 machine to an FP32 machine, and the difference in efficiency was almost exactly 16x. So that's part of the gain we had. The next biggest part of the gain, I'm breaking the 1000x down here. So 16x of the 1000 is due to number representation. Then 12.5x is due to complex instructions. So it turns out RISC is a bad idea for deep learning, because even in a GPU, and I'll have a slide on this in a second, which is very efficient compared to a CPU. We don't have any branch prediction. We don't have any speculation or out of order execution in our pipelines. We have very simple pipelines. The cost of fetching, decoding the instruction, and fetching and storing the operands and the result wind up dwarfing a single operation by about 20x. So if you do a single operation at a time, the way the RISC philosophy tells you should do, you're going to spend 20 times as much energy on overhead as you are on the payload, right? So what we want to do is have complex instructions that do a lot of operations. We started this in the Pascal generation with a dot product instruction. DP4 is a 4-element dot product, so it does 8 operations, 4 multiplies, 4 adds. And then in the Volta generation, we introduced HMMA. This is a half-precision matrix multiply accumulate instruction. It takes 2 4x4 FP16 matrices, multiplies them together, and then sums the result into an FP32 matrix. And so that's 128 arithmetic operations that you can amortize that instruction fetch and decode over. And at that point in time, the overhead of the instruction fetch and decode is now about 25%. And in the Turing generation here, we did IMMA, which did int8 matrix multiply, 2 8x8 int8 matrices, summing into, I think it's like a FP16 matrix. And there, the overhead is now down to under 15%. It's actually doing 1,024 operations with 1 instruction. So process is almost the smallest contributor here. The processes here are color-coded. 28 nanometers black, 16 is green, 7 is blue, and 5 nanometers is purple. But going from 28 to 5, I have a canonical unit I synthesize in every new generation of technology and look at the gains. The gains in energy efficiency, which is really what I measure against, have been about 2.5x, going from 28 down to 5 nanometers. And we're going to get about 10% going to 3 nanometers. So that 2.5 will go to whatever 2.5 times 1.1, so 2.8 or something. Once we drop down to 3, and we get 2x from sparsity. That was the jump. Part of the jump from Turing to Ampere was introducing this 2-to-1 sparsity, where we basically, since we're multiplying weights that can be made much sparser than 2-to-1 in most cases, we can now basically use the arithmetic opportunities that were going to be multiplied by 0 to do something else. And I should add that in addition to our improving the hardware, the model efficiency has also improved enormously over this period of time. So here's a slide on building complex instructions. So it turns out that if you normalize everything to 45 nanometers, because I have lots of data on 45 nanometers, I always like to flip back up to that. Doing the instruction fetch, decode, operand fetch, and result store is about 30 picojoules of energy. If I compare that and say, okay, I'm going to do a half precision floating multiply add, that's a 16-bit operation. That's going to be 1.5 picojoules for basically 2 operations, a multiply and an add. My overhead is 20x. When I move to the Pascal generation, I'm going to do 8 operations with the half precision dot product instruction. Now I'm down to 5x, sort of 1/4 of the amount, but I'm still spending way more overhead than I am on payload. And this means there's an opportunity for a dedicated hardware accelerator to do better. Once we introduce the matrix multiply instructions, we're within 15 or 20% of having all the energy going into math. And at that point in time, you really aren't going to do any better hardwiring an accelerator to just do deep learning. You're better off having a programmable engine with relatively big, complex operators, things that do, on the order of 128 to 1,024 operations per instruction. And so you won't do any better, because there's overhead for hardwired accelerators as well. You're not going to do any better building a hardwired accelerator. Now I have all the power of a completely programmable engine with huge libraries developed over the years behind it. This is sort of where we are today. This is a Hopper H100. I need to update the slide because we just publicly announced the H200 at Supercomputing, I think Monday this week. It's, the way to think about it is if you have sparse, which is typically the case, it's 4 petaflops of FP8 or int8, sparse, and it's, I think the new one is actually something like 4.8 terabytes per second out of 141 gigabytes of HBM memory. It also has 900 gigabytes per second of NVLink ports, dissipates 700 watts. It has a transformer engine that basically scans the data if you're doing transformers and decides when you can use FP8 and when you have to use FP16 by looking at the dynamic range on the fly. And one thing I'm very proud of is I wrote the original proposal and did the research for the dynamic programming instructions that are in here, because at the time I was doing a lot of work on bioinformatics, and I wanted to basically make this as fast as a dedicated accelerator for doing Smith-Waterman, the sort of core, gene alignment algorithm that's at the core of many bioinformatics programs. And so we got some instructions in there that make it, about 50 times faster than previous generation GPUs, and perhaps several hundred times faster than a CPU at doing Smith-Waterman. A core metric that I like to compare things on, and you'll see me show this metric later with some other things, is that doing int8 or FP8, it's 9 teraops per watt, 9 trillion operations per watt on deep learning. Lots of people like to compare back to the Volta generation where that number was, like 100 gigaops per watt. But this is the thing to beat if you want to compete in deep learning inference. Unfortunately, we can't sell these to China right now. And despite the fact that I spent a lot of time in Washington explaining why this is a really bad idea, the only real effect of this export control policy has been to cause thousands of Chinese programmers that used to write software for our machines to now write software for the Huawei and Byron machines. And basically, it's going to hurt U.S. industry in the long run without slowing China's AI progress down one bit. But the people in Washington don't like to hear that. So we've gotten 1,000x over the last 10 years in single GPU performance, but the gap that was created going from AlexNet to GPT-4 is 10 to the 8th. So where does the other 10 to the 5th come from? And it comes from parallelism, from using multiple GPUs. And the parallelism starts out with a single model, what we call model parallelism. When we take the model's a bunch of matrices, and we'll take a single matrix and we'll split it up over a number of GPUs. We call that tensor parallelism. We'll usually split it in a single dimension. So for example, we'll put so many columns of the matrix on the first GPU, so many columns on the second, and so on. And then we'll take the different layers of the model, and we'll call that pipeline parallelism. We'll split those across a number of GPUs. GPT-4 takes about 20 GPUs to hold one copy of the model. And then, for training, we then use what's called data parallelism, where we're training it on a bunch of tokens. We'll take some of the tokens, we'll send them to the first plane of GPUs here. Some more tokens, send them to the second plane. Some more tokens, send them to the third plane. And after finishing each of these mini batches on its respective plane, we'll do an all reduce operation and share the weight updates so they all learn from all of the tokens. And so scaling up is how we've done the other orders of magnitude, say also scaling up in the amount of time. And so as we scale up, we start by taking that GPU I showed you, the Hopper GPU, and a DGX H100, or the new ones are H200 servers, have on this board 8 of those GPUs and 4 NV switches. So they're connected together with our NVLink network, which allows you to do loads and stores from one GPU to the next. It basically looks like one big GPU with 32 petaflops of sparse FP8 performance and dissipates a little bit more than 10 kilowatts. The next step up is you'll take a bunch of those and connect them up with either NVLink switches that I'm showing here, or InfiniBand switches, which look very similar to this. They tend to be big pizza boxes with a bunch of OSFP connectors in the front. This is where you plug in either electrical or active optical cables, and then switch chips. And this one has 2 switch chips in the box. Here's a picture of a DGX SuperPod, and this is actually relative. I forget how many GPUs this one is, but people have built clusters up to on the order of 60, 70,000 GPUs that are used for deep learning training. They're too busy training large language models to take them offline for the amount of time it would take to run high performance WinPack, which is what the annual supercomputing competition is. Actually a pretty meaningless benchmark because it tends to measure your peak FP64 performance and not all the other things that make a balanced machine like memory bandwidth or network bandwidth. But if you took one of those machines offline for a little while and ran HPL, it would be the #1 machine on the top 500 list. But people are having too much fun doing AI to do that. So here, what you see is in each rack, we have 5 of those. The things with the gold faceplates are those 8 hopper HGX boxes that, 8 by 5, that's 40 GPUs per rack, about pretty close to 60 kilowatts per rack. And then in the middle here, we have a bunch of Mellanox quantum switches that are connected on the back panel that you don't see here by active optical cables to these individual boxes. And what's nice about this is if you buy all these components, you rack it together, you cable it up, you run the diagnostics, get rid of the cables that don't work, you turn it on, and you can that day be doing deep learning training jobs because all the software is integrated. To give you a comparison, when we built some of the big supercomputers, at Oak Ridge and Livermore with NVIDIA GPUs, they were typically 6 months from racking it up and getting all the hardware working to running productive jobs on it, because there's many layers of software that have to be brought up. Because we sell these pre-configured with all the software, it's immediately productive. But this is how, at least, that 10 to the 4th of that remaining 10 to the 5th gets done. And when people push it out closer to 100,000, that's where the rest of the 10 to the 8th comes from. Now, so far I've been talking about hardware. It turns out that anybody can, the core thing here is doing a matrix multiplier, right? Anybody can build a matrix multiplier. I used to teach the undergraduate hardware design class at Stanford. If I was to assign a typical Stanford undergraduate, design me a matrix multiplier, it would be a homework assignment, right? Overnight they would do it, turn in the Verilog the next day, and it would be a pretty good matrix multiplier. What makes those matrix multipliers useful is thousands of person years of software, literally probably millions of lines of software. And so since we started working in AI, I kicked off the first project in AI at NVIDIA in 2010. I remember very distinctly, I had breakfast with my Stanford colleague, Andrew Ng, who at the time was doing a sabbatical at Google Brain, finding cats on the internet. This is the famous, cat on the internet thing. Now, why people really want to find cats on the internet is beyond me. But what I remember from the conversation is that it took 16,000 Xeon CPUs to find one cat. And I said, I bet we could find the same cat with fewer GPUs. And so we repeated the experiment. I signed the guy at the time was a programming language researcher called Brian Catanzaro, who had some background in AI and was very excited about the project, to work with Andrew. And he basically replicated that with 48 GPUs. Of course, Andrew then went to Baidu and stole Brian to go to Baidu with him, but we got Brian back later. But the software that came out of our cat finding project turned into cuDNN. So we started building the software stack for AI, probably around 2011. So that project got kicked off. And since then, we basically built all these layers. The base layer of cuDNN that sits in the bottom with every generation of GPU, they're very efficient GEM modules. These are the software matrix multiply kernels. Layered on top of that, how to fuse layers together to avoid unnecessary memory bandwidth, taking parameters off chip and then bringing them back on through an optimizing piece of software we have called TensorRT, up to the application level layers of the stack, where we have things like NeMo for building conversational models, Modulus for doing physical simulations like fluid dynamics and heat transfer, using AI, weather prediction, and the like, Clara for medical things, Drive, which is our autonomous vehicle package. So application layer optimization, the core underlying thing, and support for all of the major frameworks like PyTorch and TensorFlow. I think we support like 12 frameworks. And it's not static. So this, it turns out that the real test of whether somebody has an AI capability is how well you run real applications. A good proxy for that test is the MLPerf benchmark suite. There's an independent organization, we participate in it, Google does, lots of people do, where there's a set of benchmarks posted. There are 2 runs per year for training, and I think there's more than that for inference, or maybe it's 1 for training and 2 for inference. And at the training 2.1 thing, we plotted this thing, and there's two takeaways here. One is that Hopper is a lot better than Ampere used to be, but the other is that Ampere is a lot better than Ampere used to be. This is exactly the same hardware, and running BERT, it's 2.5 times better. And that really shows the importance of software in this thing. If you sort of take naive software and just run it on your matrix multipliers, you get naive performance. And it takes a fair amount of optimization to really get the performance up there. So I try to track the different MLPerf results. The most recent training one just came out on November 8th. And unfortunately, I had to clip the article before it started talking about how great NVIDIA was. I did get, no, I didn't actually, but if you go back to the last one, you see the NVIDIA is the top performing accelerator. NVIDIA H100 Tensor Cores deliver the best AI performance. But this is also good to track the fact that other people are showing up in these. For a while, we were basically the only, we and Google would show up. There'd be a bunch of stuff on whatever the latest NVIDIA GPU was and a bunch of stuff on the Google TPUs. But now we're seeing, the Intel Gaudis, and we're seeing some Qualcomm things and actually some Huawei accelerators showing up and doing reasonably well. And so it's, I sometimes feel like, we're in that movie. I forget actually what the movie is, where the protagonists are running really hard and behind them is like a horde of barbarians chasing them. And because everybody out there wants our lunch, and sees this huge market for AI hardware and figures they can make matrix multipliers too. So as we run ahead of the, barbarian horde, how are we going to stay ahead? So let me talk to you a little bit about future directions. So one thing I use to inform where we should be investing, research dollars to build both better AI hardware and software is, where the energy goes, because that's really the key commodity. How can we get the most performance on training and inference of AI models, per unit joule? And what this shows is, where the energy goes in an accelerator we recently built that I'll actually show you later, something called Magnetic BERT, which is an accelerator for doing large language models. And the biggest chunk is almost half, 47%, is in this data path plus MAC. So it's doing arithmetic. So we really still need to focus on doing arithmetic more efficiently. And the way we've historically done that, going from, Kepler to Hopper, was reducing precision from 32 bits to 8 bits. And we have at least another jump there. I think 4 bits will work if you do it right. And I'll talk in a little while about how you do that right. And there are a bunch of ideas on number representation that I'll go through, but it boils down to doing cheaper math with smaller numbers. Also, if we can exploit sparsity, we will make that math part smaller, right? If we're doing 2-to-1 sparsity now, we're doing it only on weights. If we can exploit some sparsity in the activations, if we can go from 2-to-1 to 4-to-1, we could wind up doubling our performance with sparsity. Almost all the rest of this, everything except for that little 6% green slice, is memory access. And so it's a weight buffer, the accumulation buffer, the input buffer, and the accumulation collector, which is like a little small buffer in front of the big buffer. And what we need to do there is both smaller number representations, make those memory accesses cheaper, but also the things we can do with circuits on memory. And so to give you an example, these memories are read mostly. Typically, we're staging through a deep memory hierarchy. Almost all the energy is in this bottom level. There's very little up in the global memory where we're pulling the stuff out. And so we'll read from that global memory right into these little, say, the weight buffer once. And then we'll reuse that weight 32 or 64 times. So we're writing once, using it, say, 32 times. I'm willing to spend more energy on the write if I can save on the read. And one way to do that has a little bit of an area penalty is to have separate bit lines per cell. These are small memories. Some of them have like 8 words, right? So I'll have 8 separate bit lines. And when I write, I don't just energize the cell, I energize the bit line. But now every time I read, I don't need to energize the bit line. It's already been charged to the value of the number that I want to read. And all I need is a little multiplexer at the output of the memory to select that out. And I've reduced my read energy dramatically at some cost in area and some cost in write energy. For communication, it's a small part, the 6% data movement. We're looking at circuits as well because it turns out that if you were to assign a student the job of coming up with the most energy expensive way of communicating a bit, they would probably come up with the way we do it today, which is use the power supply to signal a 1 and ground to signal a 0. I mean, that's enough energy to fry a cow, right? If you're looking at it from communication theory and you're asking what EB over N0 do I need to signal a bit across the chip, you could probably do it with a few millivolts, right? You don't need a volt to do that, right? And so if I can come up with more efficient ways of signaling a bit across the chip, that 6% can go to 0. Unfortunately, it's only 6%. But there are other rooms for cleverness. And one thing we're very excited about is using the emerging 3D packaging technology to stack memory on top of the arithmetic to reduce the amount of distance that it has to go. I'll talk about some of these moving on. Let's start with number representation. So there are really 2 attributes of a number system. One is its cost and its accuracy. Let's start with cost. There are 2 aspects of cost. One is the operation energy and the other is the movement energy. The movement energy is just directly proportional to the number of bits. The wires and the memories don't care what those bits mean. They just care how many bits you're moving around. So moving a 8-bit number costs twice as much as moving a 4-bit number. The operation energy depends a lot on what the representation is. And I've illustrated a bunch of representations here. And what you're really doing with these representations is trying to trade off the operation energy against the accuracy. And the accuracy has 2 dimensions to it. The dynamic range, the range from the smallest number you can represent to the biggest number, and the accuracy, how much error you have in doing that representation. The way to think about it is what a number system does is it maps numbers from the real number line to representable numbers. And when you do that mapping, you pick the closest representable number and you ask, how much error did I introduce? Usually as a percentage of what number you started with. So let's talk about that. Here's a chart that shows the dynamic range and error of a bunch of number systems. Only talk about some of the ones that are up here. So sort of our standby is using an integer representation. And I'll show this. And integers are really bad. And the reason is they've got really cruddy dynamic range, right? That's the green thing here. So the dynamic range is really small. And they have really big error. That's the red thing. And I've scaled it so that error gets bigger going to the left. So a small red bar is worse than a big red bar. So bigger red bars means more accuracy, more digits of precision. So, compared to the competitors, in particular compared to an 8-bit log system, an 8-bit integer system is awful. It's got way less dynamic range, and it's got, way worse error. Now, it turns out that if you're worried just about minimizing the error for a given number of bits, it's hard to build a lookup table. So if I train a table, and with backpropagation, you can train anything, right? And so actually in 2015, Song Han and I wrote a paper that was an iClear on how to do optimum quantization. And we basically trained a neural network to backpropagate into a 16-entry table. So we would come up with the optimum 16 values, the optimum 4-bit representation to represent the weights of a network. And I'll show you a graph of how that looked in a few slides. And it was great. This is absolute. We could get accuracy that was better than what you would get with, I think it was actually better than what you could get with 7 bits of integer and better than you get with maybe 6 bits of a log or a floating point representation. The problem was it turned out that the math was very expensive. To actually accurately represent those symbols, we had to decode that table into 16 bits and then do 16-bit math, which was very expensive compared to the alternative. So it was a great paper, but a really bad idea. And then there are all these people who like to try to mimic the way biological systems do their computation, and they like to use spiking representation. So here you represent an activation by basically the number of pulses that appears in a certain point of time. So imagine I want to represent a number between 0 and 128. The 128 would be 128 pulses in a certain time interval, and the 0 would be none. And on average, you'd have 64. So that's 64 toggles. That's the equivalent to 128 transitions. On average, if I have an 8-bit number, 4 of the bits will transition. So it's 32 times the energy of using an integer to represent something. So it's really hard to make spiking energetically come out. And then probably about once a month, I get somebody coming to me, with a startup company they want NVIDIA to acquire that's doing analog neural network computation. And everything looks really good when you look at the basic operation. After all, if you have a resistor, think of it as a conductor, and you apply an activation as a voltage, it does multiply essentially for free, and produces a current that you can then sum onto a line. So you can do, weight times activation, summing all those together onto a bit line for almost no energy. Almost no energy probably means, order of tens of femtojoules. But then you have to do something with that. And the problem with analog values is you can't really store an analog value. There aren't really good analog storage devices. And you can't really move an analog value. It's actually very hard with high precision to move an analog value from one place to another. So what everybody does right at that point, after they've done these very cheap, vector matrix multiply operations, is they put an A to D converter. And we wrote a paper in DAC in 2019 analyzing the essential cost of doing that A to D conversion. And you wind up with on the order of 1 teraop per watt after you account for that conversion, compared to 10 teraops per watt for Hopper and 100 for an accelerator I'm going to talk to you about shortly. And actually with way less real precision, even though many of them claim 8-bit precision, they wind up getting somewhere between 3 and 5, depending on whose proposal it is. So somehow, oh yes, because I moved to a PC. So if this had been on my computer, you would see a big blue thing with 2 distributions. So if you prune networks, the area around 0 is excluded. And just imagine there's a blue thing here, representing this sort of bimodal distribution with 2 normal looking like curves, centered around here. And this is sort of illustrating the difference between, say, an integer representation of 4 bits and our symbol representation of 4 bits, and that the integer uniformly samples this space. And so it's got you're wasting a lot of data, symbols out here, data representations, where there aren't there are values out to 0.06 here, but there aren't very many of them. So you're using a lot of your symbols representing a very sparse part of the space, and not a lot, during, where this actual curve is, there's maybe 3 or 4 data points. Whereas with the red dots, which is the trained quantization, you're sampling it much better. If you don't prune networks, you tend to get distributions that look like this. They're centered around 0. And the point to take away from this is that small numbers matter a lot. And so you really want to make sure your number system's accurate and near 0. So let's talk about some different ways of representing numbers. And one way that I'm very fond of, although I have not yet been able to talk our product people into putting it into a shipping product yet, is the log representation. So when many of us started school, calculators were excessively expensive. So you did all of your calculations with antiquated things that looked like this. And you would do a multiply by essentially adding 2 logarithmic representations. The scale on this slide rule is logarithmic. And so if I, slide the 1 across, say I wanted to multiply in this case, 1.2 by, say, in this case, it's 1.12 by 1.3. I would put the 1 by the 1.12, I'd go over to 1.3, and I'd read the answer off. And I'm basically multiplying 2 things by adding the logarithmic representation of those things. In terms of how the bit layout is, this is the log 4.3 representation, right? So I have 1 sign bit. It says whether it's positive if it's 0 or negative if it's 1. I have 4 bits to the left of the binary point. That basically says, to what power of 2 do I multiply the number by? And then I have 3 bits to the right of the binary point. So I'm actually representing it as log, not base 2, but of log base 2 to the 1/8, right? So if I have, 0, 0, 0 in that EF field, it's just powers of 2. From, if it's 0, it's 1. If it's all 1s in that 4-bit field, it's 2 to the 15th. But if I start putting things in that EF field, then I start to have to multiply a power of 2 to the 1/8 in there. So 2 to the 1/8 or 2 to the 2/8, 2 to the 3/8, and so on. Now, this is great. It's got a dynamic range of 10 to the 5th. I can represent up to 2 to the 15th. A worst case accuracy is 4%. I'll show that in a plot shortly. And compared to integer, where I get 3 orders of magnitude less dynamic range and way worse worst case accuracy. And it turns out one of the reasons why this has been a tough sell is that floating point, which people are much more familiar with, is almost as good because it's a semi-log. The difference between floating point and this is what you do with those bits to the right of the binary point. Here, there are additional log bits, and so the spacing between each symbol proportionally gets larger as you move along. With floating point, the spacing with each symbol is the same as long as the exponent is the same, and you're basically using an integer representation to interpolate between those 2 points. So I like to do this graphically. So remember, what we do with a number representation is we're mapping the real number line, that's actual value on the x-axis, to the nearest representable number, right? And that's the closest representable value on the y-axis. With a log representation, you see the wiggly line starts out with really small wiggles. The size of the wiggles are the error. So when I have small numbers, I have small error, and the error is sort of a constant, with this 4-bit representation, a constant 9% across the entire number line. The error gets bigger as the numbers get bigger, so the percentage error is the same. With integers, the wiggles are the same size everywhere. And so with big numbers, I have a relatively small error percentage-wise. But with small numbers, I got a really big error, and the biggest error is sort of trying to represent 1.5, right? Where if I round it down to 1, that's a 50%, or 0.5 error out of 1.5, which is a 33% error. Just for comparison, here is the 4-bit log representation, the 4-bit floating point representation. And you see, it's not that much worse. It's, 13% versus 9%, because the wiggles are the same size for a while, and then they get bigger for a while, and then they get bigger yet, and then they get really big, right? So you get the same size error over a range of numbers rather than having each number getting its own size error. So with log numbers, multiplies are cheap. They're just adds. And by the way, that means that the cost of them doesn't scale quadratically with the number of bits. It's linear with the number of bits, because that add is linear in the number of bits. And it's substantially cheaper to do an add than it is a multiply. The problem is it's hard to do an add in the log system, because what you have to do is take that log number, convert it back to integer, add it, and then convert it back to log. The good news, though, is that you can think of the add as having, the converting the integer as having 2 parts to it. The part having to do with EI, that's just a shift, right? That's a power of 2. And the part having to do with EF is a lookup, right? You have to look up in binary what is 2 to the 1/8, 2 to the 1/4, 2 to the 3/8, and so on, depending on what that number is. And what's neat is I can factor that out. And so let me explain what I mean by that. Here's a figure from a US patent. The patent information is down there, where you basically take the number I'm trying to sum, and I break it into 2 parts, right? So the part to the left here, I'm going to feed through, and the part to the right selects in this demultiplexer where I'm going to feed it through to. So I'm going to basically take all of the things with an EF of 0 and feed them into this partial sum accumulator. And I'm going to take the quotient and just shift 1 by that. So it's just rotating a 1 to the right position and adding it in. So now this is just the cost of selecting which partial sum accumulator and then adding a 1-hot number in. And by the way, you can exploit the fact that it's a 1-hot number to make that add less expensive than it would otherwise be. And the reason for that is, on average, if I add a 1-hot number in, I will toggle 2 bits. I'll toggle the bit where I added in, and then on average 1 more bit, because half the time it's only 1 bit. A quarter of the time it's 2 bits, an eighth of the time it's 3, and so on. And if you take that series out and calculate its expected value, on average you toggle 2 bits. And at the end, after I've done this sum, and you're typically summing tens of thousands of numbers, I do 1 multiply by this constant that I have to look up. And that makes this very cheap. So that's in my mind, that's sort of the best root number representation. But whatever number representation you use, there's a separate question, which is how to scale the values you're trying to represent to best fit into that dynamic range. When we first started playing with deep learning, we did this in a very naive way in 2 ways. The first is we computed 1 scale factor per layer of the network forward and another scale factor per layer of the network coming back. The other thing we did that was very naive is we scaled it to exactly fit the largest and smallest number in that layer. And here's why that's a bad idea. So imagine that, so we did the thing on the left. So basically, suppose our biggest number is 0.8 and our smallest number is minus 0.8. So we pick a scale factor to basically fit, in this case, let's say I have an int 4 representation to fit the 16 values shown here by the red lines between that. This gives me a really large quantization noise. On the other hand, I have the flexibility to say, I'm going to scale this to 0.2 minus 0.2. And what I'm going to do by doing that is I'm going to make my quantization noise, which is the space between these red lines, much smaller. But what I pay for that is any values out here, I'm going to saturate to my largest representable value. And that's clipping noise. So it turns out what I want to do is trade off clipping noise against quantization noise. And I actually sort of brought up this idea of optimizing this at a meeting. And I said, well, it would be really great if we could compute what the mean squared error is of doing this, but I don't think that's possible. And a new hire we had, this really brilliant guy, Charbel, comes back like the next day with the integral up there that I had to stare at for a couple hours before I could figure out what it meant. And so it turns out you can actually calculate by doing this integral what the mean squared error is of choosing a particular clipping value, which is in this case S. If you unfortunately calculating the integrals is kind of expensive, and for activations you need to do this on the fly because their value varies dynamically. It turns out though that this iterative approximation to computing S actually works pretty well. And if you do that approximation, a couple iterations, you converge, and you'll pick your optimal clipping scaler. And what you're doing is you're saying, let's pick this one because it's low enough for me to point at. What you're saying is, let's say I have the 4-bit value here, and my numbers, run from 4.2 as the maximum value. If I pick a clipping scaler of 4.2, it means I'm not doing any clipping. I'm going to represent that 4.2 number exactly. So my clipping noise is 0, my quantization noise is large. As I clip to 3 and then to 2, my quantization noise goes down by a lot. So the overall mean squared error goes down, and my clipping noise is going up, but it's still small compared to the quantization noise. When I hit this minimum is where the clipping noise and the quantization noise are the same. I should say their contribution to mean squared error is the same. And at that point, that's the optimal clipping factor. So we can compute that. And in this case, it's a big clip. It's like, a clip of 4 to 1. And if you look, I don't have the 5-bit line on here, but it's giving you a better result than doing 5 bits without clipping. It's giving you almost 6 bits without clipping. So it's giving you almost 2 bits more precision by just optimally clipping. So that's one of the cards that we're now playing to sort of get more out of the bits that we do have. The other card we're playing is to figure out how often to apply these scale factors. So it's not expensive to apply a scale factor, and so doing it only once per layer is not nearly enough. It's like one of these things, if something is fun, do it more often. It's fun to apply scale factors. Let's do it. If you do it every number, that's expensive, right? Greatly increase it. But if you do it, say, once every 32 numbers or once every 64 numbers, it's not so bad. So what we're going to do here is if we're multiplying input activations by weights, rather than having a single scale factor for that, we're going to break these into vectors of length v going in this channel dimension. And we're going to apply a different scale factor for each vector. And we'll support this in our hardware by adding 2 multipliers. This one here that actually is used every sum, I should say. Most of our core things, we're actually doing a 2-dimensional set of multiplies. So we have a vector and then a set of vectors. And so we're typically, if those are like 16 and 16, we're doing 256 multiplies per cycle. We're doing 1 extra multiply over those 256 to scale it. And we're going to take the weight scale factor and the activation scale factor, multiply them together around that, and then use that to scale that overall product. And if we do this, what we're doing is we're saying, it used to be we would optimally clip over the entire distribution of the layer. I really should just draw a smaller normal curve here. If you take 32 elements, actually the distribution winds up not looking so normal because that's a pretty small sample. But if you take 32 elements, you just get a tighter representation. We can then optimally clip that and just wind up with tighter clipping. And again, we get order of a bit or 2 more effective out of this. So now when we talk about sparsity, this is a figure from a paper that Song Han and I had in NeurIPS in 2015. And what we showed in that paper is that neural networks are inherently sparse in the sense that if I take, say, a multilayer perceptron like this, the average multilayer perceptron, I can lop out 90% of the weights. And if I then retrain it with a mask that holds the weights I've lopped out at 0, I will get the same accuracy I got with the original network. For convolutional networks, I can lop out about 60 or 70% of the weights without any loss of accuracy. So, we wrote that paper in 2015, that's 8 years ago. And since then, I've been banging my head against the wall trying to actually build hardware that exploits this with reasonable things. So we actually wrote a follow-up paper that was in ISCA on something called the efficient inference engine that basically built dedicated hardware to walk the sparse matrix, compressed sparse row structure. And it actually worked great. And it gave very efficient results if you were building scalar processors. The problem is the efficient way to do these calculations isn't to build scalar processors. It's to build, matrix processors, things that basically, compute, a set of vectors simultaneously and compute, take that two-dimensional set and compute one sum from that. And so we were able to show, we're very efficient compared to a scalar processor, even at 50% density. I remember when we originally wrote the sparsity paper, one of the reviewers said, "Oh, this is completely impractical because everybody knows it doesn't pay to use the sparse matrix package until your density is down to like 0.1%. And in software, that's true, but in hardware, I can have a dedicated unit to walk the pointer structure and look up where that next non-zero is, and basically that winds up costing very little energy. The problem was doing this in a regular way, in a two-dimensional parallel way. And so the only thing we came up with that actually worked was what's in Ampere and Hopper, which is this two-to-one structured sparsity. The archive reference is here, where what we basically do is we train our weights densely, and then we do the typical pruning. We basically take the smallest weights, lop them to zero, in a pattern that we insist that there be no more than 2 non-zeros in every 4 elements. And that's actually not hard to do. If you could have lopped out 9 out of 10 of the weights, not lopping out 2 out of 4 is pretty easy. And if you can't do this, you just do a dense calculation. But then you retrain the network with this mask, and then you compress it. So I only store the non-zeros along with some metadata that says which ones those were. Now I can use that metadata to fetch the activations that line up with the weights that are non-zero. The other activations I don't bother to fetch. And now I do a dense multiply, and I can do that dense multiply, in 2 dimensions, a array of vectors, and compute those sums in parallel. And this winds up being super efficient. The problem is I'm giving up a lot of sparsity here. I'm not exploiting any sparsity on the activations. Doing that requires doing an intersection then of what are the non-zero activations with what are the non-zero weights. And we had some things that we thought worked pretty well there until we actually started doing the very detailed simulations accounting for glitching, because the problem was that as you did this intersection, you would keep changing your mind on which things you wanted to select as inputs to the multiplier. And every time that switched, you would be basically pumping another number through the whole arithmetic pipeline. And that glitching wound up just making it energetically very unfavorable. So we're still looking at how we can exploit more sparsity. And this is one of the areas where there's big opportunities to get more efficiency, because this, I think, we're getting close to mining out the number representation vein, but we're not nearly close to mining out the sparsity vein of efficiency. So let me talk a little bit about accelerators. We tend to use accelerators as a way of prototyping ideas, seeing what works, and then moving it into our products later. So in deep learning, we've Song and I built this efficient inference engine. This was the thing that walked the sparse matrix structure. That pointer even and pointer odd is basically the pointers that say where the non-zero elements are in the matrix, and they were in separate memories with dedicated units walking them. So every cycle, we would get actual payload data to go into the arithmetic unit, which is in the middle there. Joel Emmer at NVIDIA, working with VNC at MIT, built Iris, which experimented with a lot of interesting ways of tiling the computation, breaking a matrix computation down into smaller pieces in a way that minimizes the data movement. And they coined terms like row stationary or output stationary or input stationary about how to minimize the movement over this array. We did another attempt to do sparse right with something called the Sparse Convolutional Neural Network Accelerator in 2017. And the idea here was eventually every weight has to hit every activation. So we just multiply them all together, and then also multiply the metadata, or actually we add the metadata together, figure out where they're going to land, and sort everything out by doing the scatter add operation on the output. So everything looked really good up until that scatter add operation, but you don't want to move your irregularity to the output, because that's where your precision is the highest, and irregularity there costs you the most, right? So if we're starting out, we typically will start out with like 8-bit weights and activations, but accumulate to 24-bit. So we're basically moving all the irregularity to where it's the most expensive. That one not being a great idea. Symbo, which we did in 2018, it was the best paper at Micro, was mostly an experiment in scalability. So we built a two-dimensional array on each of these chips and then built a multi-chip module with 36 of those to show scalability and actually to debug a lot of chip-to-chip technology. It's actually now shipping in product. That's the one thing that's transferred out of here. So if you think about what accelerators do, a lot of that is already in the tensor cores or the matrix multiply units. They do special data types, like FP8 or FP4 if we go down to that level, and special operations. And by doing these, they can do in one cycle, which otherwise take hundreds of cycles. And this is a huge efficiency gain. So think about an IMMA instruction. It's doing 1,024 operations in a single cycle with a single instruction. The next thing is that there's massive parallelism, thousands of fold parallelism that's going on in parallel. And this tends to give you performance, but doesn't actually improve the efficiency. We typically optimize the memory, right? So we're feeding these operations out of dedicated memories, and that's hugely important. Even if you take the operations and make them zero time, if you're going to main memory to fetch all of your input operands, that's going to swamp everything else. You need to be feeding things out of small dedicated memories. And you get rid of the overhead, and I'll explain that 1000x efficiency gain in a little while. And the one thing, we've seen this less for deep learning than we have, for example, for the genetic computations, but the algorithm architecture co-design are really important. When we started doing our genetics accelerator, we took, I think it was Minimap was the alignment software that everybody was using at the time. And we found that if we just built the best hardware we could for it, we could get like a 4x over running it on a CPU, because we could make the dynamic programming part run super fast. But the part that comes before that, the seeding part, involves main memory references. You basically are looking up in a big table, where this particular 11-mer appears in your reference genome. And that's an expensive operation. There's no way to make it inexpensive. Big, large table accesses in main memory are expensive. But what we discovered is we had made alignment go so fast that we could get by with less efficient seeding. We could take a worse false positive ratio out of the seeding stage and just fix that with more alignment. And by rebalancing the algorithm to what the hardware was capable of, we went from being 4 times faster than running it on a CPU to 15,000 times faster than running it on a CPU. So what you have to realize is today's algorithms have been very highly optimized for the cost structure of running on conventional hardware. And if you're building new hardware, you need to revisit a lot of the decisions that were made in those algorithms. So I've been building fast accelerators since 1985, some simulation engine, some signal processing engines, and then for the last several, deep learning, and then the bioinformatics accelerator. And Satin is actually a SAT solver accelerator. And they all exploit, among other things, getting rid of the cost of interpretation. So this is a graphic that really drives the point home. I can tell people 10,000x, and it doesn't drive the point home as well as this does. So this is for an ARM A15, which is a very modest out-of-order processor. The ratio is much worse with an Intel Xeon or with an ARM Neoverse, which is what we have in our Grace chips at NVIDIA. But even on this very modest out-of-order processor, the cost of fetching and decoding the instruction, which involves looking up in a branch prediction table to predict, even before you know it's a branch instruction, to predict whether it's a taken branch or not, and then fetching the instructions, decoding them, reordering the instructions in a reorder buffer. You have to look which physical register your logical register is in and go through that mapping and do all this bookkeeping. And all that bookkeeping is the blue area here. This is at 250 picojoules to do an instruction. Now, suppose your instruction is a 16-bit integer add. That's 32 femtojoules. All this is normalized to, I think this was done like a 28 nanometer process. Yeah. And that red dot is 32 femtojoules to the blue area of 250 picojoules if linearly, if area is energy. And so that's an awful lot of energy to spend on overhead. It's kind of like a big corporation where you have a couple people doing the actual work and then lots of bureaucrats, trying to decide what order to do the work in and what should be produced. And then when you build the accelerator, you try to figure out, what different things cost. And the real takeaway from this, I don't want you to have to realize this, is that adds are cheap compared to multiplies. So look at a 16-bit add as 0.05. And, the 16-bit multiply I didn't put in here, but it's going to be, about 4 times that 0.2 for the 8-bit multiply. So it's going to be, about 0.8. It's 16 times as expensive to do the multiply as the add. Well, you should think that's about right? Because that multiply, I'm doing, 16 adds to add the 16 sets of partial products up. That's why log numbers are such a great idea. But the big thing to take away from this is to realize how expensive it is to read a memory. To read 32 bits out of a small 8 kilobyte memory is more expensive than the most expensive math operation. And it's orders of magnitude more expensive than the inexpensive math operation. You really have to avoid going to memories at all and just feed arithmetic results right one into the other to get good performance. And it's worse as you go up in larger size memories. So that 5 picojoules per word was reading, a 32-bit word out of a small local SRAM, an 8 kilobyte SRAM. If instead I need to go to a sort of an on-chip SRAM that may be, megabytes or tens of megabytes, it winds up being an order of magnitude more than that. Now, it turns out you build big SRAMs out of little SRAMs. Nobody builds one array that's 10 megabytes because you have a limit on how many bits you can put on a bit line that's typically like 128 or 256. And there's some sensible things about how long a word line you want to make. So you typically build these things up out of 8 kilobyte arrays. So the way to think about that 50 picojoules is it's 5 picojoules reading the array, and it's 45 picojoules sending the address to that array and getting the result back. So it's memory energy is mostly communication energy. And that's true accessing off-chip DRAM as well. Reading a DRAM cell is a very inexpensive operation, even including the sense-amp to multiply that back up. But getting that read from that sense-amp, to the pin of the HBM chip across the interposer into the GPU, into the SM that's accessing it is where the bulk of the energy goes, and simply getting the address out there. So it's really important to keep things local. And there is, in all of our deep learning accelerators, there's a layer under this. This is an 8 kilobyte SRAM. If we're doing like 8-bit weights, we have a 64-bit SRAM with like 8 words sitting right in front of the arithmetic units. And that's our bottom level of the memory hierarchy that we're getting most of our reuse of. So let me talk about our most recent 2 accelerators. This is one we published in 2019 called Magnet. And what we did is we didn't actually build an accelerator. We built a program that searched the design space of accelerators that kind of look like this. So it varied various parameters. It could vary the memory hierarchy, how many levels of the memory hierarchy, how big each level was. And the bottom of it were these, weight buffer, input buffer, and accumulation buffer. And there actually was an accumulation collector we added to do kind of a hybrid, tiling in the sort of Joel Emmer Vivian C style. And then each of these address generators fed a vector MAC, and we searched along the dimensions of how many lanes of vector MACs we have. Remember, we're doing a matrix operation here. So we have a vector of some number of elements, and we were searching along the dimension of how many elements per vector and then how many lanes of those we have. So it's a 2-dimensional multiply add that's going on in parallel. And searching across these, we wound up getting order of 20 terops per watt, about twice as good as Hopper is today, on a wide range of neural networks. But the next level, and this is the one we reported actually at the VLI Circuit Symposium in 2022, and it's in the Journal of Solid State Circuits this year, the longer version of the paper. We pulled a bunch of things, and so we used the same magnet search procedure to search over this design space, but we combined the vector quantization I told you about, putting a scale factor per 32 element vector, and the optimum clipping to basically let us get by with an int4 representation. And we held ourselves to holding accuracy. So it's an int4 representation, I think with no more than a 0.5% accuracy lost on BERT and BERT large. And we put a bunch of special functions here. There's a paper about something called softer max, where we use soft max, but we use powers of 2 rather than powers of E, which makes life a whole lot easier. The result is essentially 100 terops per watt. Doing the vector quantization at 0.46 volts, which is basically about as low as we can operate our SRAMs. We can operate the logic a lot lower than that. And there's an interesting question about splitting supplies and running your SRAMs on a separate supply, but we didn't play that card. And the energy overhead to support the vector quantization is tiny. It's less than 1%, and it gave us huge dividends by letting us go to 4 bits where we otherwise would have needed 8-bit representation to get the same kind of accuracy. And so this gives you an idea that there's at least another order of magnitude beyond Hopper that we can have for inference without loss of accuracy by simply playing some more number representation cards. So I think I'm way over time, at least in part because my computer wouldn't work. So let me wrap up. So, deep learning was enabled by hardware. These algorithms have been around for 30 years. The data, the large data sets needed to train them have been around, for probably, close to, easily 10 or 20 years at the time the GPUs came along. But until we had hardware that was fast enough to train a big model on a large data set in a reasonable amount of time, it didn't click. But once that hardware was there, it really ignited this fuel-air mixture, and things have taken off in computer vision, in large language, language modeling, and speech recognition. AI is transforming almost every aspect of human life. And as it does that, we feel continuous pressure to make our hardware better, because what people can do is limited by the hardware available to train and run inference on these models. And under that pressure, we've improved single GPU performance 1,000x over the last 10 years, with only 2.5x of that coming from better process technology. The rest of that has been cleverness, better number representations, complex instructions, and the beginnings of exploiting sparsity. I think there's a lot more to be done on both number representation and sparsity. With number representation, logarithmic numbers, optimum clipping, and VS quant, none of that is in a shipping GPU today, although we've demonstrated it in our accelerator experiments. I should say at NVIDIA, we're very fortunate. We produce a lot of big chips. We tape out a couple big chips every year, and there's always empty area on these big chips. And so I go around to the people in charge of the big chip projects and sort of negotiate, how many bottles of wine do I have to give you to get a couple square millimeters in the corner of that chip, so that we can put some of our research experiments on there, and we tape those out with them. And so we're able to, fabricate the stuff in 5 nanometer and 3 nanometer without paying for a mask set or even the shuttle charge for those technologies. What we're doing is taking a lot of these things with better number representation and better approaches to sparsity and prototyping them on these accelerators to sort of prepare ourselves for how to get the next couple turns of 2x every year in future GPUs. So this is where I live, up on the shores of Lake Tahoe. And with that, I'd be happy to take a few questions.